Well, I guess we can get started. This afternoon we've got two related talks. Ollie and Mike are going to go back to that about suspension and surgery. It's all really cool about surgery.
Thank you. Can you guys hear me? Oh, no. How about now? Okay, great. All right. Thank you. Thanks for the invitation. It's a great pleasure. Give it a talk here. So far, they have been great. I mean, I usually say it at the beginning of the talk, but this time I really mean it. So today I'm going to talk about some work with Mike Mueller-Eismeyer, and part of this is also based on some joint work between the three of us, which I will elaborate later. Let me start by just some basic facts from third-degree three manifolds. So there is this elementary but important theorem is due to the correlation Wallace, which says that if you have a connected, oriented, closed three manifold Y, can be obtained by surgery along. Now, and one question that you can immediately ask here is that can we replace this link L with a knot? Can we always assume that L is a knot? And this version of question you can immediately answer. You can say that no. The point is that if you have a three manifold Y, which is given by surgery and a link L with number of connected components of L big N, then this implies that you have some constraints on the homology of your three manifold groups of linear C and surgex into the first homology there. Okay. So, if you have a three manifold with a implicated with large S1, and since that that's required, it has a lot of summands, then you cannot construct, you cannot get it by surgery on it. But based on this, you can refine this question and how about if Y is an integer homology sphere. So we're getting some abstractions from that. So let's look at the simplest case that there is no abstraction from integer homology sphere, the simplest version of first homology, and see that in that case we can get it surgery on and on. And well, you would say that okay, so when you look at things with integer homology, we could use first homology. Now there is no such thing, but let's go to the next thing that's like algebraic homology. The first thing that is an algebraic homology. I look at the fundamental group of the three manifold. Can we use that to get some abstraction? And yeah, the answer is yes. So if you have the three manifold, which is surgery on a link with L connected components, we can say that I1 of this three manifold Y has weight N, which means that I1 of Y can be normally generated by any elements. So we already have some tool which could be useful for this kind of question. But it turns out that showing that like some Abelian group has some weight larger than something is actually quite a difficult question. Maybe it's even more difficult than the original question here. In fact, there is this famous group theory question due to Riegel. And spell that correctly. Yeah. It says that any finitely presented group any finitely presented perfect group have weight 1. And remember that perfect here means that like the commutator is equal to the whole group. And yeah, if the answer to this question is yes, then there is no hope of getting that, because if you get pi 1 of the integer homology sphere, that's all the perfect group finally presented. And this would tell you that that doesn't work. But it is very likely that the answer is no. The issue is that we don't have the right kind of tools to get lower bounds for the weight of groups. So okay, so like basically, for this kind of question, all of our tools from algebraic geometry fail. Let's get to some three-manifold topology tools, and just going to leave a bunch of results in this direction. In the following, I'm going to always assume that y and integer homology is here. There's only one place where you won't be much that current focus indicates that y is active homology is here. And first, resolve in the direction of the other question due to Gordon and Luki, which says that any reducible integer homology sphere 5 if that's assumed that y is an integer homology sphere reducible, then that'll be okay. By surgery on. In fact, their results is much stronger. They basically say that y not necessarily your homology sphere, if it's given by surgery not and it's reducible, then one of the submen has to be the length space. But that cannot happen if y is an integer homology sphere. Later, so now it's yes, all right, so the answer to this one is no. Clearly here we're using another property of our three-manifold. So now let's assume that y is the addition to being integer homology sphere, it is irreducible. And this is where our debate came into the picture. So we constructed in 1993, 1997, he constructed reducible integer homology sphere. In fact, in the second paper, if this guy to be an hyperbolic y such that y is not circulating along it not. And more recently, they construct many examples there are many such examples. Talks about. There are examples that on applications, so particular examples, they also have weight one. Their fundamental groups, they all have weight one. So personally, all these fundamental groups is something about certainly the number of components that will be involved for this. All right, so let me, motivated by these results, we call some definitions A. Let's say that for a three-manifold y, S of y is the minimum number of connected components of a link such that y is the same by circulate along and we get to define some variation of that. So here, by surgery, I mean integral surgery. So all the components of our link are integral frame. And also I look for dense surgery. And ask what's the minimum number of components of the links so that y is obtained by dense surgery along L. And because any surgery is an instance of dense surgery, then they say that SC of y less than or equal to. Yeah, so what they construct this example basically if you answer one of the previous questions, and because there should be some conservation of period problems because otherwise it would be bad for our topology. So he introduced proposed another problem. So he asked are there any homology here which is reducible, maybe even orthogonal integer homology sphere y such that the surgery number of y is arbitrary large. It's greater than some even number n. Positive integer n or n to the n, we have reducible electrolyte of integer homology sphere y, so that it is greater than n. Or even better, S here Y. And our main result created by this question which says that if we have let's take your three manifold Y to be connected sum of n copies of the Poincare homology sphere, if Yn connected sum of n copies of P. And let W be a four manifold which fills this three manifold, four manifold. And the boundary of W is equal to Y. And I need to put some technical condition on the homology of this guy. The first homology of W with integer coefficients is two torsion free. So as not two torsion. Then claim is that we should have this W should have some B minus of W at least equal to n, the number of vector components of Yn. Of course, there are examples. I'm using the orientation of Poincare homology sphere that you have negative definite manifold bounding Yn, so you can come up with examples that B plus is equal to 0, but you cannot make B plus small, so it has to be at least equal to n. So, I mean, just as an immediate observation, you can see that in this theorem, we can replace Yn with any other integer homology sphere Y that is homology covariant to Y. Okay. And in particular, we can, for any integer homology sphere, you can find hyperbolic three manifolds which are homology covariant to that three manifolds. So in particular, we can assume Y. Any questions about this statement? So as a corollary of this theorem, we can say that the third degree number of disconnected sum of n of the Poincare here. The same as the tensor degree number is equal to n. We can also say Y is homology covariant Yn this time we can update it exactly what we can, but that is as the y of greater than s two, as the y of greater than s01, necessary number is greater than.
The question, I mean, if you answer the question affirmatively without the answer, you never know you answered.
Is there a general question or
You have to know that you can produce for ADN something, surgery number, angle surgery number. Are is based, is n. Because you can convert it into review. Surgery number also knows that.
well, you want to use like one of the sound off.
Yeah, you'll have to be.
But like you might make it hard. You might have a density number like I put it in the medical where the answer really that answer really number one, but you have to do this really rational coefficient. And you want to convert it to integer surgery that becomes really a lot of
But I mean, like, if you know that for every n there exists a manifold whose integral surgery number is n, doesn't that imply that the same as your neighbor?
no, like it could be like actually there are also a few number of delegates on the second. But yeah, I think you have, I mean, this is relevant. I think that doesn't, you need a little bit more than that. In fact, I should have said that Dave's example will also like he had to test the white with that one. And let me not go into too much details, but yeah, so another remark that I want to make here that you can also ask whether if you take like connected sum of a bunch of non-trivial three manifolds, like n non-trivial three manifolds, is the surgery number at least n. And we don't have, the right tools to answer the question. But at least we can say that in the case that you take that if non-trivial manifold, you convert homology sphere answer. That as y. Let me just make a word about how to take this roller that here. Let's start with that easier prediction so that we want to show that s of y n is greater than or equal to n. I mean, you can show that y and conquer all these various one direction here is clear as a y and then this y is greater than or equal to n. Here, so let's say that y n is surgery integral surgery. Then what you can do is you can construct that value to be using a four wall and two handles along, then two handles along the lines of them. With a ring which is given by then from this you can see that B plus and B minus the W, right? The secondary number is residential. And another thing which is correct is that the first homology of that with Z multi coefficient, this is trivial. So the technical condition and the first homology is also satisfied. And okay, then sorry, that's not equal to the number of factors. But the theorem will give us a lower B minus, so say that these are the number of factors has to be greater. So the answer to the number. This is related to the math question that if y10 is certainly some L or not L is rational frame, give me the answer. It's the nice exercise working with continuous and so on to see that if you use a bunch of to show that this three manifold is also certainly some other link where L prime is integral to frame. And more importantly, like if you apply this construction to L prime, now it's integral to frame, so we can start a format like this. This W prime is given as above for L prime. Then B plus of W prime. We can do it for B minus W prime is at most the same as it's equal to it's at most the same as the number of components of the link that is okay. So now we can just follow similar argument as the first case to see that the density number is also at rest. Okay. Any questions up to this point? This is the end of. I'm going to focus for the rest of my time. I'm going to focus on the tools which are used in the proof of this theorem. Yeah. I didn't tell you why. I said that we can do this, but it's just that next is what we can keep practicing. Then we can use one for the sum of moves. Comparing is L prime to some to turn the L to some L prime which is integral to that, and then you look at the link form of that it has B minus in form the number of that it was also related to that was the example.
But there's no way to control, how many, like what those, like those manufacturing there's no way to control the length of the continued fraction expansion. Just knowing that you have a molecule.
Maybe someone is the fraction in the item of all right. So I mean, not surprisingly, the tools here coming from integer homology sphere. It's coming from Instanton floor homology. So, and I want to just go through some basic, just talk about some aspects of Instanton floor homology, which initially you see that it is going to be mod to Instanton homology working with the mod to coefficient. Which initially you're looking at, okay, everything should be like fraction coefficients, but it turns out that this is not exactly, it's not quite the case. One place that mod to Instanton homology is gonna one reason that mod to Instanton homology behaves differently compared to rational coefficient case is because of topology of SO3. So let's just look at SO3 for a second. So, I'm gonna look at the homology groups of SO3, and for this talk, I'm going to be interested in the case that we're working with mod to coefficients. So SO3 is still nice enough that you can write down some CW complex structure on it, so that at the level of cell structure, the differential is trivial. Homology is the same as a cellular complex. And also, like, this feels what it is, like, it's the exterior algebra over two generators, chi1 and chi2, over extra coefficient where degree of I is equal to I. In fact, you can also take chi3. And also, there's a chi3 here for the parallel. Okay. Yeah, so it has 4 elements, and chi1, chi2, and chi3 are the elements here. But because it's a topological space, the homology has the homology group has some interesting structures coming from cup product. But because here I'm working with homology, is going to be law of the cup product, so we can look at the diagonal map from SO3 into SO3 and SO3, and that induces some math. I'm going to from now on, I'm going to use, there was a request from my colleague bring lambda, so I'm just going to stick to my promise. I'm going to call it lambda, and so this induces the map from lambda to lambda tensor lambda, and there's just thinking it's the transpose of the usual cup product. So it's lambda from chi I, it's just going to be chi A tensor chi. This might show up later in my talk, depending on if you can make it to the end of the talk. But there is another important structure which show up immediately, and it's related to this algebra structure that here I already mentioned some algebra structure and had the meaning here. So like we have a product map. Now I'm using the fact that SO3 is a group, so we have map. Yes.
What is this? Is this meant to be homology?
It's homology. Right now, think about it as just a vector space over F2. It has 4 elements: 1, chi1, chi2, and chi3. But it has a, here I'm implicitly talking about some algebra structure, and the algebra structure is coming from the product and SO3. You have a multiplication map which induces. Yeah, sorry. This is chi1 times chi2. Particle degree of chi3 is 3. And yeah, so the product structure is a map used by multiplication. Like just for instance, like chi1 squared is equal to 0, chi2 squared is 0 for degree reason, chi3 is chi1 times chi2. Okay. I mean, you already see, some more structures when you work with multiple coefficients. So this is, if you were working with rational coefficients, this string would be just this would be a exterior algebra with 1 element, which is going to be a degree 3. But now because we're working with H2, there are additional elements here. Now let's assume that now we have another topological space X, where SO3 is acting on it. And I'm going to also assume that we already implicitly took a cell structure on SO3 and talked about cellular homology. The point is that I'm using SO3's RP3, and I'm just using a standard cell structure on RP3. So here, let's say that you also have an SO3 action. vector 3 times x, and I'm also going to assume that this is cellular. So x here is theta. Okay. So this induces a map from by looking at the induced map at the level of cellular chains. So you get a map from lambda tensor cellular main complex X to. So that tells us that this is this guy together with this differential and this map, the DG module. The DG algebra. The part for this DG algebra lambda is trivial, the differential is 0, and like this guy. And why we're talking about this, because in instanton floor homology, you can also naturally construct some space X, which now is going to be infinite dimensional, but it has an action of SO3. So the option of this is that you expect a singular algebraic structure in that form. But why is that space X instant floor theory? This is the space that you would do floor theory on. So it's like some infinite dimensional space that basically you want to do more homology of that in order to get instant floor homology. But at the same time, we want to keep track of some additional structure that we would get from the given that from the SODH. So let's say now again, let's go back to the three manifolds. Say that y again integer of this here, and define some space near y. This is going to play the role of x for us. In order to define it, I need to fix a base point on y. And you might wonder why, SQ2, let's go back to SOD. The point is that SOD is the accurate group of SQ2. SQ2 mod the center is called SOD. But what is this space Py? This is a space of pairs a connection. And SU9 and phi is a sort of framing. There's a map from framing at the base one. There's a framing at the base. It's a map from the basic one, but not quite the basic one. Not quite the fibers. We look at the acronym of this guy. Here, I think there's a plus minus one at the base one P, and some isomorphism to SOP. It says the aggregate is going to be some SO3 1 over y and restriction of that. So now, like we can get some SOP action on this guy, which is change of range. And this action is also like part of the point of fixing this frame is that to make sure that this is You're talking about by this let's say it's a fact. We're looking at why. What I told you was not quite correct. That means it was just too big. You have to modify some action. And here, this is action of the automatism of the models. And the point of talking about the technique here was that make sure that this action is because if I didn't do it, you get a thing first. Regular, but at the same time, feel that by remembering the sense of reactions. There is some sense of reaction, so motivated by, and maybe I want to speak about the structure of this model, is that there is a transition functional, So here, so let's say the transition is functional and beta of y is associated in there. The point is that the transition function doesn't really that unread something my interpretation. So just because now you have order and needed kind of this here, they expect that the package of this kind of work theory gives you some kind of similar side. This kind of work theory, which is some sort of maybe you make a more serious part of this guy. Give us complex equal to y. Really, if I were at 2, I'm going to do this one very strong. Why am I taking going on? It's complex. And it's a PG module. Might say a few words about the definition of this guy. Are you going to do that? Maybe a few words, yeah. Well, let me just say that this equation of y is at the level of vector space. What it is, the field of y is actually direct sum of copies of lambda for each irreducible flat connection on y plus one element which is coming from the trivial connection. So maybe we should just say that this is a copy of our underlying link and 2. So the action of lambda here is trivial, like only one action trivial here. So this is coming from the trivial connection. And maybe as a remark, that in a case, this is when y is integer homologous sphere. In the case that y is a rational homologous sphere, even already here, things become a little bit more complicated. We have also U1 flat connections, which are some kind of reducible connection on y. And each of these guys contributes. You can still define the analog of the string, and each of those guys would contribute a copy of lambda of current. Okay, so there is no current. Yeah. I mean, you could consider other bundles. And no matter what you pick, you would have, sometimes you have some kind of connections which are behave like trivial connections, some kind of connections behave like U1 and others. All right, and there is also some sort of functoriality going on here with respect to coordinates. So the simplest version of functoriality is with respect to homology coordinates. So if W is a homology coordinate from some integer homology sphere to another homology coordinate. Then what you can do is that you will get an associated y and y prime that is the modules, and you can also associate the coordinates and get a DG module. Coming from so it's like coming from your coordinate and again instant compare. And an important property of that map is that FW satisfies the property that you have this spatial component theta coming from Y. You can ask what is the image of this guy. And in general, it has some interesting contribution from the irreducible guys, but at least something that you can always say is that the pairing, the coefficient of theta on the trivial connection here is always very important. And this is something we have to do with working with homology coordinates. Okay. So that would suggest some straightforward way of trying to get some homology coordinates and invariants. I think following some general strategy, it goes back to the other math stuff again. You can define some omega lambda in some local chain commands. So you basically consider C2, E2, not just abstract space of BG modules. Over lambda. And I would also say that C2 has similar shape as C field of integer modulus here, meaning that you always have rank one summand which is coming from F2. So there is only one dimensional F2 and the rest of it is just 3 over lambda. And by some relation, it also motivated like this, that so like two such DG modules are related to each other, we can negate. And at times, the DG module and are similar to F down. So basically, you just look at the space of all DG modules, and they have a certain kind of structure, which models are chain complexes coming from Istanbul model. There is another combination which is modeled also by cohorts in that. So this just by thinking about C tilde y, so C tilde y is omega lambda value multiple coordinate. So you can just say that it's a C tilde y, there's a element here, and just because by definition, we might have this sort of relation that you would expect from coordinate to get some coordinate. This would be great if you knew what kind of lambda is. What is any of your text, you could say that this is too complicated to teach. Two reactions are kind of complicated to give up, and you try to define some variation of that. So we can define a variation of omega lambda, the same definition as omega lambda, that we replace lambda with this secret between this lambda. There is this algebra lambda with u by exterior power 1 by 2. I can just get now lambda finally close. And just because lambda continues and lambda city or Pavilion, and that's going to be our definition of
value because this it's gonna but you don't know that this is like a homomorphism like we do with the other literature.
Yeah, if you're asking that question, that's a great question. I have to say something more than here. Now, unlike this original set omega lambda, this other set is has nothing to time. We can identify the integers. Okay. And part of what we get this subtraction will give us we obtain the z value if you obtain z value all t for the variant. And if I read so we obtain some variant Q3 which satisfies the bunch of nice problems. And the first one maybe are really set over there, like if y and y prime are homology coordinate to each other. Then that implies that Q3 of y equals Q3 of y prime. And the second one is that the second. Q3, if you reverse the orientation, it's equal to minus of Q3 of Y. Unfortunately, this is not going to be, I don't know, unfortunately or fortunately, this is not going to be a homological cobordism invariant. But what is true is that in the case of the three manifold that we talked about, Q3 n copies of the concurrent homologous sphere. So this was Yn. That's what we call Yn. So this is equal to n. So this is like based on with just going to write during the time I'm just going to write so ME and S, Scaduto and micro. And some other key property of this invariant, which I think Mark is going to talk about in this talk, is some sort of behavior, which this is, you should think about this QC as some sort of Rorschach type invariant or fraction type invariant. This is analog of invariant, X invariant, mode, or H invariant, Instantons, like monofocal homology. But all of those guys you could control whenever you had a negative definite cobordism. But those invariants, they're kind of difficult to control over whenever you want to compare the invariants of 2, 3 manifolds which are related to each other by negative definite cobordism. But something which holds for Q3 is that this satisfies some property which would allow you to do that kind of control. So this is like the conditions that I'm going to list here. It's going to be similar to the conditions that I wrote in the theorem at the beginning. So if W is a smooth manifold, smooth core manifold with H1 of W with Z multi coefficient is 2, sorry, with Z coefficient is 2 torsion free, so it has no 2 torsion. Then we can say that Q3 of Y shifts a lower bound for B minus of W and an upper bound minus B plus W. So that's the kind of inequality which basically you can get the theorem that I mentioned at the beginning by combining Z and 4. How much time? All right, I have only 2 minutes. Let me just maybe just say a few words about connected sums of Z manifolds and the unit structure here. So the connected sum theorem here, which is also used, basically this is the main input for this part. It's actually a little bit more subtle. You know, like this is one of those instances. I mean, like when I started working low division project, I figured everything in algebra college. And this is one of those instances we get humbled by, you know, like algebra college. Like there is something interesting going on. SO3 here is too complicated. And connected sum, like you would be expecting some sort of connected sum here says that like C tilde, just break it up. It's one thing. The C tilde connected sum of to 3 manifolds, we expect that this is chain multiplicated by the tensor product of C tilde, the sum. Is it a Asian molecule? Turns out that this is not quite very straightforward, and part of it is that because it's really it's complicated, so you have to either work very hard understanding how the specifically like the diagonal mass and expressions of diagonal mass, or you know, have to collaborate with, and you might miss the second possibility. But yeah, in anyhow, like so, what happens is that you don't, at least you get some technical ones at the market, but that it's not, it's a technical ones from A to B, so you have some variable returns, which could be annoying, but like in the case of concurrent homology sphere, it's not that annoying, so you can actually compute it. What this is what I just going back to Matt's question, like if you get a read, I mean, you can get a read structure like just any test for that here, but maybe just if you want to get a logical homomorphism, if you want to get a homomorphism from logical potential to this, maybe you have to below what is here. So you probably need some sort of like stronger relation where this some strong. We will have to double this. All right, so running out of time.